All right, look at example 5. Now, so far, I've given you simple example whereby there's only one state. So this is the first time there is two state. And you look at this example. Now, basically require you to write a MATLAB program. All right, because ultimately the command filter will be a algorithm. You need to run it on the computer. Every sample, if the sampling interval is 1 second, then you have to run one time every sample. So this would be the model of the plant as well as the command filter. And all the numbers are given here. So simulate one run for k equal to 0, 1, and 2. So I wrote the MATLAB program for you. It's just 2 pages. You go and take your MATLAB, copy it, and then run it. It's just 2 pages, very easy. Now, you can see that the first part is just writing down all the parameters, whatever is given. A is given, C is given, and this is to calculate the command filter gains. So now here, because the first part asks you to run only for k equal to 0, 1, and 2. So that's why n is equal to 3. It's because MATLAB count from 1, 2, 3. So though on paper write 0, 1, 2. So MATLAB is 1, 2, 3. All right, which means when k is 1 in my lecture notes, it is considered k equal to 0. In MATLAB, k is 1. All right, so it's just MATLAB and the textbook. The textbook like to start from 0, and MATLAB cannot start from 0. So that's all there is to it. Now, the main thing is, you see, calculate the command filter gains. I told you before, you can calculate the, okay, no, I will not do that. Okay, this part, calculate the command filter gains. So you see, this correspond to me saying that, I tell you before, this one, KF, K, and then PK and PK plus 1, you can calculate at home. You don't need measurements. Only when you calculate X hat and X hat plus 1, then you need the measurement Y. So that's why if you don't need the measurement, you can calculate at home. If you know all the A and the C, you calculate at home. So that's why this one, calculate the command filter gain. The loop here, it just loop by itself. All right, and calculate without any measurements. Okay, so is k equal to 1, 2, and 3. Capital N is 3. Okay, so you got 3 command filter gains, 3 sets of command filter gain, KF, KP, PM. All right, which correspond to here, KF, K, P, and PM is this one. All right, so then after that, they say, okay, then the plant starts to run. All right, when the plant starts to run, you will get your measurement. All right, the plant is given here. So from here, you will get your measurement Y. Then with Y, you feed it to the command filter equation. So here, you basically get your measurement Y, and then feed it to your command filter equation, X hat and XK plus 1, which is this one and this one. Okay, and then the rest is just do some plotting. Also take this opportunity to introduce to you that, let me go back. Because last time all the examples are one state only, this noise here is a scalar. All right. Now, but here, because there are two state, last time it was a scalar, so R1 is written like that. This is the expectation or the mean of W squared. All right. Now, if it is a scalar, if it is not a scalar, then you will have to take the mean of this. Wait, you take the mean of this. All right, multiply by its transpose. Okay, I shouldn't write like that. You take this column vector, multiply by its transpose, which becomes a row vector. Then after that, you go and find the mean, which is also called expectation. So now you see this is half t squared w. This is tw. I show you how to do it. All right, here R1 would be take this half t squared w tw multiply by the transpose. So if you do that, then you multiply, you will get a 2 by 2 matrix. Then after that, take the mean, means the mean of each of the element in this 2 by 2 matrix. So basically, it's the mean of W square, mean of W square, mean of W square, mean of W square. All this, of course, depends on t, whatever t is. So since the mean of W square is 1, which is given in the question, all right, the variance is 1. All right, I think there's a typo here. This typically, all right, what we will write is sigma square is variance. So that sigma by itself is standard deviation, and this is variance. All right, since I call variance, I should type it as sigma square and sigma square. Unless I change the word here with standard deviation, sigma W equals to 1. All right. If just to make, if I write standard deviation, then it's correct to write the, all right, since I write variance, I should put a square here. Okay, so since this is 1, this is 1, this is 1, so this will be 0.25, this is 1.5. So this would be your R1. R2 is the same. As far as my scope is concerned, Y will always be a scalar. So V will always be a scalar. So V squared, the mean is 1. You can see this calculation of R1 inside my MATLAB program also. Let's see that. This is the R1. All right, this is the R2. All right, then the rest are all trivial. So you must type this in, because this later on at the end of tonight, I will go through the project. You have to do the project, and this MATLAB program is useful for your project, or you use it as the starting point of your project, because the Kalman filter is written for you. All right, a process is written for you. So to do your project is on Kalman filter. So definitely you need to use this Kalman filter equation. So I purposely give you this MATLAB so that for your project, you won't be lost. I'm giving you a good starting point for your project. All right. So, and then repeat the simulation for 100 runs. So here is just one run for let's say last time I like to say k equal to 0 is midnight, 1 o'clock, 2 o'clock. So this is only one night. So you do the for 100 nights. So every night, 1 o'clock, midnight, 1 o'clock, 2 o'clock. Then tomorrow, 1 o'clock, midnight, 1 o'clock, 2 o'clock. Then Sunday, midnight, 1 o'clock, 2 o'clock. You do it for 100 days. If you do that, ask you to plot. So I show you the answer here, you plot, all right? Here would have 100 crosses. Okay, here should have 100 crosses. Okay, then we say midnight, 1 o'clock, 2 o'clock. All right, depends on what you're measuring. If you're measuring temperature, it's easy to think. Of course, in control, then you're measuring, you could measure temperature in control. Then so it could be, every 1 second. So 0 second, 1 second, 2 second, whatever. Okay. Then after that, the last part C is to Part C, instead of 100 runs or 100 days, ask you to run for 10,000 days. All right, if you run for 10,000 days, then after that, you show that P12 is equals to this. All right, P last week, the tutorial question show you is the mean of the expectation error. Sorry, variance of the expectation error. All right, this is what MATLAB I want you to verify in MATLAB. You remember last week tutorial questions? I tried very hard to tell you this. Show that this is actually this. All right, what is this? Expectation. This is variance. All right. If you square this is the true state. This is the estimate. So the difference between the true state and the estimate would be the estimation error. Since you square it and mean it, so this will be the variance of the estimation error, and it's always equals to PKK. So last week tutorial is to show using algebra. So today verify using MATLAB. So this one, your MATLAB will calculate this. Then use your MATLAB to calculate this. Okay, means what? Let me draw for you clearly. Calculate this means what? Okay. It means that you see there are two states here. So this one, all right, I showed you before. It is this one here. All right, P22. So which means your P22, MATLAB will give you one value, because when you calculate, you use your MATLAB program, there's a P there. So you pick out the P22, you will get a P value here. Okay? All right, so the P value, pick out the P22, go and see what is that value. All right, this P value will have a number. Then after that, at the same time, because you will have 10,000 X hat or X, so let's go to here. All right, so you find at the X at 2 minus the estimate at 2, there will be 10,000 of them. Go and use MATLAB, find the mean. All right, this one is the same. X2, you have 10,000 of them at K2. So for this tutorial question, it will be This will be 2. All right, 2, 2. All right, but don't forget, there are 10,000 estimates. Okay, there are 10,000 true states. So find the error, square it, find the mean. All right, if you look at your MATLAB program, you are changing n run to 10,000. Then you will save here. Inside here, you will save 10,000 of them. Yes, 10,000 X save and X hat save. All right, this would be your, this would be your X hat 2, this one, then go and add your X2. All right, here of course contain X1, X0, X2. So you take out the X2 and X hat 2. All right, I've done it for you here. All right, you see, you find the mean, you find the mean, you find the mean. Okay. And then what will happen is, I think then you come out, you will compare, you will compare and find that this number here is, which is equals to, you compute this, it will give you 0.8, 0.611. This number also should be equals to 0.6, 0.8, 1.1. All right, both the MATLAB, the two way of calculating should match. This one also, P should also give you around there, because MATLAB is numerical, so you will get 0.6001 or something like that. And this is 1.009 or something like that. But then you know that they are correct. All right, these two should match within the numerical error. Okay, so that would be the tutorial. No, that would be that question. Okay, so now let's go on to look at the tutorial question. So the whole idea is to make sure you start programming with MATLAB for the command filter. Now look at the tutorial question 1. Okay, tutorial question 1. All right, so this is the plan, is also the model used by the command filter. All right, this is the process model. This is also the model used by the command filter. Then everything is standard. So there are 3 parts. Part A, R1, got noise. This is R1. The variance of W is R1. R2 is 0, which means your measurement that time is perfect. So which means in my example, you're using a $10,000 temperature gun. Okay, so find the command filter, find X hat for the following case. Now, the key thing is that after the command filter gain reach steady state, which means the command filter, the K, KF, the P, and the PK plus 1, you will find that later on when you use the MATLAB program, if you look at them, you find that after a while, K plus 1 is equal to K, which means they reach steady state. P plus 1 is equals to P. All right, you'll find that it will reach steady state. So here the question is, when after the command filter reach a steady state, what find x hat. Okay, so let's look at part A. Now, at steady state, which means then, it doesn't matter. The sampling K is irrelevant because K, let's say after K go to 10 is steady state. So small K go to 10, 11, 12, 13, 14 is irrelevant. So we just, it is equals to a constant. So KF is actually equals to KF, a constant. It will not change anymore. K is equals to a constant K. PKK is, I call it PF. PK plus 1, I call it P. So all these are constants because they reach steady state. If you do that, then you substitute 53 into 57, you will get this. Means what? You're going to look at 53. You look at 57. 57 got a K here, got a K here. You take this K, this thing, put inside here and put inside here. You will get this. Okay, I don't need to do the maths. It's quite simple. All right, 57 is the equation for P. You see no more, all the small k are gone. So it's P is equals to, no, sorry, 57 is P. So P is just equals to all this with K taken from 53. So if you do that, you will get this. Then you rewrite, you will get this. Okay, so now let's start. R2 equals to 0. So you see 52 and 54 will give KF equals to 1. 52 and 54, 52 is this. Since this is 0, and C is 1, then this is PK over PK. So it's just KF is equals to 1. So 52 give KF equals to 1. 54 will give your estimate equals to Y. 54 is this one. Since this is 1, all right, this one will minus this one. C is 1. So X hat at KK is equals to YK. So all you get is just this. So, like I told you before last week, no, your estimate will completely follow measurement Y. So this is expected because R2 is 0, which means V is 0. Then of course you look here, R2, which is the variance of this, is 0, which means V is 0. Okay. So you have your super expensive temperature gun that measures your temperature. So you will say the estimate is what you get from the gun. All right, this is what the maths will say if you put this as 0. All right, and since I say you measure, this is the true state, the temperature inside your body, because R1 is greater than 0, which is the variance of the noise here, which means your thermometer that you use to put inside your mouth is a lousy one, 50 cents only. So this got noise, this one got no noise. Of course, you follow the temperature gun. You don't go and follow your thermometer inside your mouth. Okay, so that's what it means here. So that is A. B. So now for B, you see, I told you before, P is the variance. What is variance? Variance is you square the noise, then you find the average. Oh, then square noise must always be a positive number. Square cannot be negative. So you square the noise, then find the average. So that the average must be positive because you square all the noise, it must be a positive number. So P must be positive. So now let's go back and look at this equation. Part B gives that R1 is 0. So you see part B now is different. Or they say trust the you put a very good thermometer inside your mouth, so you trust this, then R2 is greater than 0. So you got a lousy gun, okay? Lousy temperature gun here. So you are going to trust this. You are not going to trust this because here your thermometer is very expensive one, got 0 noise. So you will trust this. All right. So means what? So how does the maths work out? B, R1 is 0. So there's R1 here, you will get a 0 here. There's a R1 here, you get a 0 here. All right. So then the equation becomes quite easy. You, with all the 0, you will simplify to P square plus 1 minus A square R2. Then there's a P here, then equals to 0. So now you factor things out, you get a P here. Then inside you get a P plus 1 minus A square R2 equals to 0. So the solution is P equals to 0 or P equals to minus 1 minus A square R2. Okay, now A, the question say is less than 1, which has to be, then you have a stable process. All right, if A is greater than 1, your process is unstable. So normal control process will be stable. So A is less than 1. If A is less than 1, R is a variance. So this is inadmissible because if this is positive, you got a minus sign in front, then it's saying that P is negative. P cannot be negative because like I said before, P is the covariance or the average of the square of the estimation error. All right. So between the two, P at best can be 0. It cannot be negative. So that's why we will choose P equals to 0. All right. We'll reject this P negative. So if that's the case, P is 0. Then you look at 52 and 53, it will tell you KF and K is 0. 52, P is 0, P is here, so multiply everything becomes 0. 53, P is here, so multiply everything also becomes 0. So KF and K is 0. So that's the first thing you get. So 35 will give you the next estimate is equals to A times the previous estimate, 35. So you go and look at 35. All right, because KF is 0, so you just say the next estimate is equals to A times the previous estimate. And I say, oh, the interpretation is that this is expected. All right, because this is what the model says. All right, you look at the model. If there's 0 noise here, then the next estimate is A times the previous estimate. You just follow the model. All right, tonight your temperature is the same as last night temperature. All right, that's what the model say. Okay. If A is 1, I mean, if A is 1, then tonight's temperature is equal to last night temperature. If A is 0.9, then, you know, tonight's temperature is 9.9 of last night temperature. It depends on A. But it basically just follow the model. So that's part B. It's expected because R1 is 0, which means your model is perfect. Okay, these are the interpretation. So Kalman filter, on one hand, is maths. knowing to do the maths is not enough. You must understand the interpretation. No, if not, it doesn't make sense to you. The number calculated already, what does it say? So it says a lot of things. All right. So now you see the two extreme case. So C, you then look at 52, 53, and 56, you will get this. So again, it is algebra, so nothing much to say. You could look at 52, 53, and 56. You look at these three equations, you will find that, they will give you this. All right. Then after that, 43 will give this. 43 is this one. This is 43. Now, you see part C, nobody is 0. Part C is, part CA is 1. R1 and R2 are not zeros, not like part A and part B. So this is a quadratic equation. You can solve for P, all right, using the quadratic equation formula, what minus B plus or minus B squared over 4AC over 2A. So if you do that, you will get P is this. So since you get this, you stick this thing inside here. All right. Then you will get, then this whole thing will now look at this. Okay, again, it's algebra. You have to go home and stick in the algebra to get this. And just do it once to convince yourself that this is correct. It's correct, I know. This. So now, for A equals to 1, so you put 1 here, 1 here, 1 here, 1 here. They ask you to plot this against lambda. Lambda is R1 over R2. So if you plot, you will get this here. Lambda is R1 over R2. Okay, now, so from there, what can we say? Interpretation again. All right. If lambda approach infinity, this is equals to this is equals to this. All right. We know that this is always equals to this. All right. Last week, I used algebra to show. Today, just now, the example 5, I tell you to go home and run the MATLAB to show that MATLAB calculate this and calculate this, they are the same. Now, how does the plot shows that this equals to this? Because when you plot this versus lambda, PF will be equals, PF over R2 will finally be equals to 1. All right, when lambda equals to infinity, you see here is approaching 1. I can't because if you continue to plot until maybe, I don't know, 10,000 or 1 million, you'll find that this will then go to 1. All right, this will go to 1. Okay, which means when R1 will be equals to this. So which means this means that R1 is very large or R2 is very small, which means either this is, which means basically you trust this, you don't trust this, because lambda is R1, which is W variance, over R2, which is the V variance. All right. So if it's infinity, means you are not going to trust this model, you're going to trust your measurement. If that's the case, then your measurement error is nothing but R2. your estimation error variance is nothing but R2. Okay. On the other hand, when lambda is equals to 0, just remember lambda is R1 over R2, which means your temperature gun is lousy. Here is infinity. All right, or R1 equal to 0, which means you trust the thermometer you put inside your mouth. All right, you will find that you get the estimation error, the variance of it is equal to 0. This plot also shows you here. All right. Now, this one will make sense to you because if you trust your Y, this means that you trust your Y because lambda is R1 over R2. So R2 is 0 to get infinity. So your estimation will forever follow Y. And since Y has this noise, so the variance of your estimation error would be the variance of this noise because you trust Y completely. All right, so the variance of your estimation will also be the variance of your Y. Okay, so that is done. Here, all right, here I write down everything that I say so you can read, it's just, I type it down, all the things that I say. Now, one way of seeing things is also like that. You go and look at 35. So you go and look at 35. Okay, you can rewrite 35 like that. Then you go and this equation is directly copied from 35. All right, 35, you copy over. Then you rewrite, it looks like that. Then in words, the interpretation you see, your estimate, one part of it come from the measurement Y. One part of it comes from the model, the previous X. You see, this is Y, this is KF, this is 1 minus KF. So, if KF is 0.6, then your 60% come from measurement, then 40% comes from the model. You can see? So what I'm trying to tell you, answer from the model plus answer from measurement. You see? You look at how you write. This is the model, this is the measurement. So you're going to follow this Y or you're going to follow this. All right. X is going to follow this or X is going to follow this. Follow this equation or follow this equation. Which one? Obviously, common sense tells you it depends on the relative noise. Who is noisier, you follow less. Who is less noise, you follow more. That's why we always say, hey, if this 0, this has no noise and this got noise, I follow this 100%. If this got no noise and this got noise, I follow this 100%. But if this got some noise, it got some noise, then you take some percentage from this and some percentage on this, which is shown here. All right, see? Some percentage from the model, which is this one, as the estimate, and some percentage from the measurement Y. Okay, so there's the interpretation. All right, I stop here for a while, go for a break, come back at 7. Then we go on to do the next question. Okay, look at tutorial question 2. Now, in tutorial question 2, which is like that, the target or the man move at a constant speed of 1 meter. So the true state position is calculated like that. So which means if you start x is 0, then let's say k is sampling interval is 1 second. So if you start x is 0, so k equals to 1, the 1 second, this would be at 1. Then after that, 2 seconds, this would be at 2, 3 seconds, this would be at 3. All right, because if you start at 0, k equal to 1, this will be 0 plus 1, this will be 1. Then k will be 2, it will be 1, k1 plus 1, this is 1 plus 1 will be 2. Then k3, this is 2, 2 plus 1 will be 3. Then k4, it will be k3 plus 1, which is equals to 4. So it's basically the man walking at a constant speed. So walk here, walk here, walk here, walk here. All right. Every step is 1 meter, let's say, and the time taken is 1 second. All right, and this is what we call the true state or the ground truth. All right, the ground truth. This is true, the ground truth. So now, this would be the model of how the man walked. This tutorial question, the test is on. So you go and use a Kalman filter to estimate the ground truth. Let's say you didn't know this, you go and write the wrong model. Your Kalman filter inside the MATLAB, you go and write a model that looks like that. All right. This model basically says that at the next second, the position is basically equals to the previous second. So this is what we call a constant position model. So which means the guy is basically not moving. Of course, there's some noise. So it's like even I give a lecture here, I'm supposed stationary, that would be the best model of me. But you know, when I talk, sometimes I go like that on the right side, left side, right side, left side. So on the average, the next second will be equals to the previous second plus some slight shift, you know, or we call it noise, Gaussian random variable that models my position. All right, this would be what we call a constant velocity model. So like maybe the real man is walking like that every second. So the real man is walking like that, but you don't know. You go and write a program and you use this for your Kalman filter to estimate the real man that is walking. And your model is wrong. Your model is actually saying that the man is stationary. Sorry, this is the real man. This is your model. All right. So your model, you write, I differentiate it as all the one with prime. Okay. The ground truth are all the one without prime. And there's only one piece to do your Kalman filter beside writing down the model. There's only one other piece of information that you have. That is your measurement Y. Okay, so you take the measurement Y. So now let's see what happened. So you use this model inside your MATLAB Then part A, you say, okay, there's no noise, no W, so he's perfectly stationary. And then the variance of the measurement is 1. All right. So with that, you go and use your Kalman filter using this model. If you do that, this is the result that you get. All right. If you look, sample 0, K1, K2, K3. All right. I purposely give you numbers that are the same as example 2. So the first 3 sets of calculation are exactly the same as example 2, because in example 2, we use this model. And the measurement Y was also the same as example 2. So all this calculation, you can look back, you will get the same. Then after that, when Y start to change, all the Y's are given, then you use the model, you continue to calculate. You will find that I will not go through the numerical calculation because we go through many times. Right? You find that your estimate will go like that. All right. The estimate will go like that. We go and look at the estimate. The dotted line here, let me see. The dotted line would be the true state X. The crosses are the measurement Y, which you use inside your Kalman filter, your MATLAB. All right. But because you use the wrong model, your X hat that you estimate is this one. Okay. And if you remember, since you say that W is 0, finally at steady state, your Kalman filter will completely follow the model that you use, which means the next position is equals to the previous position. Okay, you can see that it is going there. You see, it is like that. If you continue, this thing will then go, then become horizontal, which means as you go on, then the next position is the same as the previous position, because you, in your calculation, you say that there's no error here. So whereas there's error in this equation, like I explained before, so at steady state, it will just follow this equation. So the next position is the same as the previous position. But the real man is actually walking. So the real man X will be like that. Will go up, go up, go up, go up, go up, go up. Okay, so your answer become further and further and further, your estimate become further and further and further away from where the real man is. Okay, so I can only do 20 steps, you know, I mean, too many, we can't see things. So if you look at the standard deviation and the average, now just to make sure we know what we are talking about. This X position is the ground truth. All right. This is the measurement that you use. Why? This is your estimate, or I should say, your Kalman filter estimate. So if you go and find your estimate versus the ground truth, you got 20 of them. you subtract the two of them, which means the circles are the estimate. So you take the circle minus the dotted line, the circle minus the dotted line, the circle minus the dotted line. All right, got 20 numbers. You go and find the average. You find that the average is about 4.9. Which means after 20 steps, the average error you get is about 5 meters, which is ridiculous. Now, this average is the average between the truth and the measurement. All right, your sensor will track the fella. Let's say you use a camera or what to measure the man. So you will get the position of the man with some error. So it's the crosses. All right, so the crosses more or less follow how the man move. Let's say your camera, you just use the camera, track the man. You more or less follow how the man move. So that's why the average error between your camera and the ground truth is about 0. All right. Then the standard deviation here you calculate is 3. The standard deviation here is 0.9. All right, which means the standard deviation would be the fluctuation between the cross and the dotted line. You square them, then you find the average. This standard deviation would be you minus the dotted line from the circle, square them, then average. Of course, this will be a big number for this 20 data point. Okay, so this is part A. Part B. Let's say now you decide that, no, part B, I'm going to say that my Y measurement is quite accurate relative to my model. So my model, the R1 is 10,000. Basically infinity. So you basically don't trust this equation. You trust this equation because R2 is 1. You say this equation very, very noisy. Don't trust it. Okay, if that's the case, you will find that I show you before, if the time I show you, if this is 0, then your X hat will follow your Y. Right? If this is perfect, I say if you have a $10,000 temperature gun, then you just say the estimate is the temperature from your measurement gun. So this is the case. The variance of this is 1, whereas this is 10,000. Basically, this is perfect compared to this. So X hat will follow Y. All right. So you look at B. B, I will not do the calculation anymore. If you want, you can double check the calculation. They are all here. You will basically find that your X hat is at the crosses. All right, because the crosses are the measurement and the circle is the estimate. So you say you have a perfect measurement. So that's why the cross and the circle coincide. Okay, you can see the number also. Can you see the number? This is measurement 4.36. This is the estimate 4.36. You see? 8.4228 is 8.4226. All right. Basically, they are the same. All right. So if you do that, then you find that, again, we see the difference between the measurement and the true ground truth. The average is about 0.0124 because the estimate follows the measurement. So you will get the same answer. So that's why, because these two are the same. This and this are the same, so they are equal. All right, so the average will be equal. The standard deviation also will be equal. All right. And if you compare this, it is the same as the previous case. All right. So in this case, your model is wrong. You say that the man is stationary. You might as well just follow your measurement, your camera. Your model is useless one. Anyway, that's why part B basically ignore your model, because part B say that your model, the R1 is 10,000. So in fact, once you put 10,000 here, this equation is as good as useless. And then just follow your measurement. And it's correct because you have a wrong model. You follow it will lead you to give you all the wrong results, like in part A. Part A, you follow the model perfectly. All right, when you say R1 is 0 and R2 is 1, you follow the model perfectly, you give you perfectly wrong answer. Okay, so now part C. Part C, you say R1 is 1, R2 is 1. So which means you like half like that. Okay, I'm going to follow the measurement a little bit, also follow the model a little bit. Okay, if you do that, then the maths will show you that you take some, which means it's like what I showed you earlier on, that, where is that? This part here. All right, KF will be some value. So your estimate, some percentage come from here, some percentage come from the previous X hat. Okay. The earlier part A and B is, part A is this, perfectly follow this. KF should be 0. Part A, KF should be 0. So this was perfectly this. Part B, I think somehow it must be this. This will become 0. So KF will be 1. So X hat will be equals to KF. No, equals to YK, and this will be 0. All right, that will be part B. So part C is that some comes from here and some comes from here. So when you work out the maths for part C, the maths is not interesting because you just run the standard Kalman filter. If you want it, the numbers are here. You can double check for yourself. The graph is here. You see the crosses are the measurement. The circles are the estimate. The dotted line, which is a perfect 45-degree line, is the ground truth. So if we find the average now is 0.5, it has improved from when you use the model 100%, it was 4.9. Now you trust the measurement a bit, you trust the model a bit, it is 0.5. Because you trust the model is wrong, so you get not so good answer also. But at least you use some measurement to help you, so it's better than if you completely trust the model. But this average is also definitely not as good as this average. All right. Then the standard deviation, you improve it to 0.55. Now, so whether this result is good or not depends on your application. Okay. Then we look at part D. Part D, you basically now, part D, R1 is 2, R2 is 1. So you change out R1 by a little bit. Then you run through the results. All right, the average has improved to 0.36. The standard deviation is 0.63. So the standard deviation has dropped from 0.5 to 0.6, but this is the mean has improved from 0.5 to 0.3. So you can use R1 as what we call a tuning parameter. See which performance you prefer. Now, this average, which is the estimation error, when it is 0, means it is perfectly accurate. All right. When this is 0 for standard deviation, means it is perfectly precise. So this average here measures what we call accuracy. This standard deviation here measures what we call precision. Now in engineering, it is very standard. In manufacturing, I think since young, you all may have given this example to you. The difference between accuracy and precision. So it's like they like to give, maybe you shoot a gun. So this is the bullseye. All right. If your bullseye is your shots, you shoot the gun, it is like that, like that, like that, like that, all around the bullseye. You find the average is at the bullseye, then it is accurate. All right. But if the bullseye is here, then this, all of them are here. All right, this same pattern. This is not accurate. All right. Then there is one thing. If the bullseye is here, and then all the 1, 2, 3, 4, 5, 6, 7, all the 7 crosses are very close. Then this is called precise and accurate. All right. Then another, the bullseye here. Then if it is here, this is called precise but not accurate. Okay. This is compare, this is not precise, which means this the standard deviation or the variance is big. This standard deviation or variance is small. This is accurate and this is accurate, which means the mean of the error is small. This one, the mean of the error is big. So these are not accurate. In manufacturing, precision usually is more important than accuracy. All right. It's quite easy to think. If I control temperature and my temperature fluctuation is like that, wow, then it's not precise. Is this type of thing here. All right. But if my temperature fluctuation is like that, then it's precise. Okay. This one, then your wafer, you go and make your chip. You can control how many nanometer you can control. This one, on your chip, some of the nanometer all very far out, the performance, everything off. Even you do temperature control, you cook food, you also some will get burned. If your temperature in the oven like that, if the temperature in the oven is like that, then is nothing, will not get burned. So this is precision is more important. Why? Just so now, let's say it's not accurate. You want to control your oven at 90 degrees. If this is 85, this is all. So you want 90, but this is 85. To solve this problem is actually quite easy one. You change the set point let's say you put set point 90, then you get 85. Then you increase your set point by a little bit. You try set point 95, maybe this temperature of your oven will go to 90. So there's a simple solution. You just shift. It's just like last time in the army, some people shoot like that. Actually, they are a good shooter. All you need to do, the rifle in front, behind, you aim like that. They use a screw to slightly adjust, left, right. So they are able to adjust, left, right, further up, down, such that this come to here. And all rifles, you have to adjust one. For each one of us, the way we do, they will adjust until this one come here, done. Those that shoot like that, you can't hit the enemy, no matter how I adjust, the enemy is here, all over the place. His head is here, all cannot hit him. All right, so there's no simple solution, except that he must practice his shooting more and more and more and more. Cannot breathe, must be strong arm, because when you fire, the guy will boom, boom. So some people the arm not strong, so cannot keep the rifle steady. So it'll be like that. So it's a major problem. Some cannot shoot means cannot shoot. All right, it's a major problem. Whereas this is a minor problem. You just the gun, the inside, the side, the front tip and the back tip, you just go and adjust. So this is also easy. Whereas if this is at 90, you get the temperature on the average. But if you go up to 100, go down to 80, like that, your process also got problem. To get from here to here, this type of variance is a major problem. You may have to change controller and so on and so forth. So in manufacturing, most of the time, standard deviation is more important than accuracy. Okay, so that is that. Now, then what is part E? So now, you don't use the constant position model. This is a constant position model, which means you are saying that the next second he is at the same place in the previous second. But use the constant velocity model, which is like that. All right. You can see that this is a constant velocity model. Means what? If you work things out, your sampling interval is 1. So if you work things out, you will see that x1 is equals to x1 plus x2. All right. So, and x2 will always be equals to the previous x2. So that means what? That means if x2 is equals to 1, then then that's all there is needed. If x2 is 1, then x1 will be x1 will be equals to the previous x1 plus 1, which is, if you write the first line here, we just write the first line. All right. If this is 1, all right, which means if this is 1, you see, forever x2 will be 1 because this is 0. This is 0, 1 here. Forever x2 will be 1. So forever, this will be 1, irrespective of what case. So this match the real man. See, this match real man. So you have used a model for Kalman filter that is able to estimate X hat because the model captures the real man model. All right. So let's see. All right. This model captures the real man model. So it will be able to estimate for you X hat 1 and X hat 2 prime prime. All right. The correct position X1 and X2. So the max, again, this because this is 2 state, so the R1 you have to do it like that. I teach you before already. R2 is like that. So the first, the model I have chosen is W is 0, so this is 0, and this is 1. So this match perfectly your ground truth model, the man walking. So if you go and where is that? So this is the result. The numbers I do it. I mean, I do a few for you. 1, 2, 3, 4, 5. The calculation is standard. Then you can see you get the best precision and the best accuracy so far. Okay, 0.27. This is basically 0. This 0.27 is the best precision so far. You see, this 0.6, this 0.5, this 0.9. This one don't need to say this 3 because the model you use for your Kalman filter match the real man. Okay, so choose your model carefully. Don't just anyhow choose any model. If your model is wrong, your results of your filter will also be wrong. Just remember, your Kalman filter basically, in practice, like I said before, take part of this equation and part of this equation as your estimate. All right. If this equation is wrong, you will take part of your wrong thing in calculating your estimate. So be careful. Okay. The last question I'm going to do tonight. Repeat Q2A and E. All right. So now, let's say from day 1, the man is really stationary. Okay. So now X is really stationary. And 2A says that he is stationary. So again, your model match your man. Just now in question 2, the man is walking. Now in question 3, the man is really stationary. And 2A Kalman filter for 2A is a stationary model. So okay, everything matched perfectly. All right. So you should be in this type of position when you use your Kalman filter. So just say things properly. So this is this is the ground truth. And this is what we call a constant position model. Okay. So the measurement, and the man is stationed at about 20 meters. So your Y is all around 20, 2017, 2019, all around 7. So you do the calculation. I do a few for you. You find that it is able to estimate your X, the ground truth, quite accurately. And because your model matches the ground truth, you will find that your PK, whatever value, I've shown this before, this PK will give you the variance of the estimation error. And then if you do the same thing, you'll find that this is 0. And this standard deviation, when you square it, is the variance. If you need to find the variance of K, xk3, you will find that it's equals to 1/3. All right. Here is not, I didn't find the standard deviation for any value of X. This is the time average, which means I basically take this, multiply minus X, take this minus X, take this minus X, minus X, minus X, square it, then divide by 20 because there are 20 of them. So that's the time average. I'll talk a little bit more about this when we go to the project. Okay, so that is that. This is the picture. The dotted line is the man is truly at 20 meters. These are your measurement, the crosses. The circle will be your Kalman filter estimates. The picture already show you your estimate is better than your measurement. All right, because you got a correct model and you also have the benefit of your measurement. So finally, your estimate, you take some from the model, which is correct. The model says 20 throughout. Your model, because basically says that it is constant position throughout, so it's a good equation to use. Here, it has some noise. So you use some from here and some from here. That's why your estimate is better than the measurement. Okay, then next. This is part E. Part E, we use the constant velocity model. You go and look at part E, 2E. Where is 2E? 2E was here. 2E, what model was used? 2E is here. 2E, this model is used. It's obvious, but this is what we call the constant velocity model. So I write it down first. Then I explain. The constant velocity model. Like I showed you before, if this is 1, then x2 is the velocity, is always equals to 1. It's always constant, which means x2 k plus 1 is equals to x2 at k. So it's forever constant. You think of this as the speed, then this is the position. So this is a speed of 1 meters per second. So that's why the position will always be, every second, this would be 1 meter further away. So if the speed is, let's say, 2, then every second, this will be the old position plus 2. So, all right, and you see the speed will always be equal to 2. If this is 2, this will be 2. And then the next k also will be 2 because x2k plus 1 is always equal to x2k. So that's why we call this the constant velocity model. All right, whatever x2 is at k, it will be x2 as k plus 1. So the velocity, we call this the velocity, will always be constant. this is the position will always be equal to the last position plus the velocity or the speed to give you the new position. Obviously, a constant velocity model can capture a constant position model. How? Very simple. As long as the velocity is 0, then xk, no, x2 is always equals to 0. So this is 0. So this is new position equals to old position plus 0. So if you use this model, you can capture the constant position, which is question 3 here. The railman is really a constant. It's really constant. So when you use this, which is, let me write things clearly, constant velocity model. Obviously, then you let the velocity, or don't say velocity, the speed equals to 0. Then this will be equals to this. That's it. All right, if you do that, the command filter will sort out the maths for you because your model can capture the real thing. So you do the maths. There. You look, the command filter also give you an estimate. The estimates are the circle is better than the crosses. All right. You have used a model that can capture the ground truth. So together with the measurement, they give you a better estimate than either using just the estimate than the measurement alone. All right, the maths are not interesting, but I think I did the calculation for you. Okay. Here I explain to you that the constant velocity model is actually can if the velocity is 0, the speed is 0, then it really captures the ground truth. Okay, now let me talk about your project. You go to the end of the lecture notes. There are 3 parts to the project. And firstly, you hand in the project during the reading week, which is more than 1 month from now. The week just before your exam, I will send the actual date. I will email all of you and submit into Canvas. All right. I'll tell you which day, what time is the deadline. Make sure you write a report, do the project, write a report, print it into a PDF file, submit into Canvas. All right. Don't submit late, because late, I will have to deduct marks. All right. And if it's too late, I can't even enter into the exam system, you will get 0. Okay, so I'll give you the deadline. You don't be late. It's already the week, because I want to give you as much time to do as possible. I already put the deadline just 1 week before your exam. Once after your exam, you have to submit the mark already. So if you submit late, I got less and less time to mark. Okay, now you see the first part, I told you the true state. This is a project. The first part, there are 3 parts. Part 1, you see this is a constant position. All right. This position is the same as the previous position. And the first part tells you to design a command filter using 5.1 and 5.2, which means, unlike the tutorial question, which is so complicated, the true man is constant. The Kalman filter model you use inside MATLAB is also constant velocity, constant position. So the thing match. So it's quite simple. If the thing match, then you write a MATLAB program, do run 10,000, all right? Then go and plot the true state, plot your covariance of your estimate error and plot KF. Okay, I think this 10,000 thing MATLAB, the starting point can be my here. The starting point can be, yeah, here. All right, this is also 10,000. All right, here is using a constant velocity model, which is even more complicated than your part one. Okay, so you do the calculation. Then after that, you plot the graph. You plot the graph, then you find the variance and the bias or the accuracy, which means the average of the estimation error. Now, what I want to say is these are time averages. Every time, last time I tell you before, I like to use this example. Just not last time, I like to use this example. Like if we take the K, you got 0, you got 1, you got 2. Then maybe at midnight you have some measurement, then you got some at 1 o'clock. You got some, these are measurement errors, not measurement, estimation errors. All right. Then I say before P, let's say 2 is the variance of this at 2 o'clock. Okay. So this PKK, if you plot a graph, since I ask you to plot and all the way up to 10,000, so this PKK, you will basically plot, I don't know what value, but you will go up to, let's say 10,000. Then this is PKK. So K equal to 0, 1, 2, 3, all the way. All right. Now, so you will find that whatever like that, told you before, you will reach a steady state. I don't know what value will reach a steady state, but after a while, maybe after K equal to 3 or K equal to 30, I don't know, it will reach a steady state. Means that it will be a horizontal line. When it reaches a steady state, it means that the next K is the same as the previous K as far as P is concerned. So now, this is the time average, whereas this is the average for 2 o'clock only. But because the average for 2 o'clock is the same as the average for 3 o'clock, 4 o'clock, 5 o'clock, 6 o'clock, if you have reached a steady state, then you'll find that the time average will also be equals to this steady state average. Okay, which means you want to find the average over here, or now you do all the way until basically 10,000. You only need to take the first sample. Let's say the first sample, the first run is this one, this one, this one, then this one, this one, this one, this one, this one, this one, all the way up here. Okay, one set of cross only, but you have 10,000 of them. You find this average, it will be equal to this average. Okay, after reaching steady state. So that's why at steady state, we should find that these two are the same. All right. At steady state, if you find P3030 will be the same as you find this for sum k equal to 0 to 10,000. Okay. So that is part 1. Part 2, same as part 1, except that we are part 1, I give you a constant position. Part 2, I give you a constant velocity model. Again, it's easy. The railman is walking with a constant velocity. Your Kalman filter also correct, also use the same model. So your Kalman filter capture the railman. No problem. So after that, you go and do your graph 4, 5, 6, 7, 8, 9, calculate all this. So everything is very easy. It's very easy. It's exactly the same. The rail project is part 3. All right. The rail project is part 3. The part 1, part 2 is just to warm you up. Just do something. Part 3 is like that. The railman walk in a circle. All right. The dots are the measurement Y and Z. So I think this is Y-axis, this is Z-axis. I gave you the numbers, the measurement Y and Z. All right. Don't know what you do. Go and find Kalman filter estimate using the Y and Z measurements. Okay, go and figure out yourself. Okay, that's where the real test is. I teach you everything already. You should be able to do it. But of course, you have to do some thinking. All right, I'll stop here tonight. I see you next week. You can start doing your project already because I finished everything on Kalman filter. Next week, I will start to teach model predictive control.